So welcome to the video lecture series on Introduction to Computer Networks. This is part 2 of our lecture on data representation and number systems for computers. So we will now move to the point where we left off, and here we go. So we have looked at so far how we can convert decimals into binary and the other way around. So now we will look at how we can convert decimal or hexadecimals to decimals. So let's try to get a better idea of what hexadecimal numbers are. So hexadecimal number is where each digit may be one of the 16 possible values. The values are 0, 1, 2, all the way to 9, and then A, B, C, D, E, F. And in hexadecimal, A, B, C, D, E, F is equal to 10, 11, 12, 13, 14, 15 in decimal values. So if you're trying to convert hexadecimal to decimal, what we have to do is that we multiply each digit by 16 to the power n, where n is the weight of that bit, which is basically the position number, which starts from 0 on the right and increases towards the left. Finally, we add all the results. So let's see how this works out. So let's convert A8F, a base 16 number, to base 10, which is a decimal number. So our tabulated value would be A8F in hexadecimal. So given that we know directly the decimal value of A to be 10, we write it out, and for F to be 15, we write it out as well, and 8 remains 8. The weights or the position numbers are 0, 1, and 2. So we start from the left, we start at the right, and we increase to the left. And the values for each of these positions is going to be 16 to the power 0, which is 1, 16 to the power 1 is 16, 16 to the power 2 is 256. So now we just multiply each of these. So 15 multiplied by the weighted value, 1 is 15. Then 8 multiplied by the weighted value of this position, which is 16. So 8 times 16 is 128. And then 10 multiplied by the weighted value, 256, is 2560. And if we sum it up, we get 2703 in decimal. So that is how we can convert a hexadecimal to a decimal number. So now let's look at the other way around. Let's try to convert a decimal into a hexadecimal number. In this case, we are going to do it by the division technique, and we have to keep track of the remainder for each division. So if we have the number 1, 2, 3, 4 in base 10, and we would like to convert it into base 16, so first, if we divide 1, 2, 3, 4 divided by 16, we get 77 with a remainder of 2. 77 divided by 16 is 4 with a remainder of 13. And then 4 divided by 16 is 0 with a remainder of 4. So we now already know that 13 in hexadecimal is equals to D. So now we create our hexadecimal number as 2D and then 4. So 1, 2, 3, 4, 1234 in base 10 is equals to 4D2 in hexadecimal. Next, as promised, we'll look at the conversion of hexadecimal to binary. And this is pretty straightforward in a way. The way that we do it is we convert each hexadecimal digit into a 4-bit binary number. If it is less than 4 bits, we fill it up with zeros. So 10AF in base 16 if we would like to find the binary equivalent. So it's going to be 10A and F. So 1 converts to 1 and then we just fill it out with zeros to make it 4 bits. 0 is going to be all zeros. Then A is a decimal equivalent of 10. So we just convert 10 into binary, which is 1010. And then F, which is equivalent to 15 in binary, this is 1111. And this whole thing together is our equivalent binary for 10AF in base 16. Now the other way around, converting binary to hexadecimal. If we follow how we converted hexadecimal binary, is just the other way around, and that is we group the binary in bits of 4 starting from the right and convert each of these 4 bits into hexadecimal digits. So let's say if you have this binary number here and we would like to find the hexadecimal equivalent, so we start breaking it down in 4s from the right. So it's 1100 and then 1011 and then we have 10. We can fill it out like this. So 1100 is equals to decimal 12, which is hexadecimal C. 1011 is equal to decimal 11, that is hexadecimal B, and 10 is equals to decimal 2. So now we have 2B C as our equivalent hexadecimal for this binary number. So we have now looked at all the possible combinations and conversions. So there is an exercise for you. You have a table where you are given a decimal number. You find the equivalent binary and hexadecimal for it. You have a binary number, 11100101. You find the equivalent decimal and hexadecimal. And then you're given a hexadecimal number 1AF. You find the equivalent decimal and binary. If I want to look at the answers, you can click here and it will jump into the answer slides. Otherwise, you can just try to work it on your own. It's better that you don't use a calculator. There is another exercise as well in the same format where you can try out, and if needed, you can try to look at the answers. So one additional piece of information which might be useful is about the base 2 and the way that we use the powers. So for base 2 numbers, we refer to powers and the preface. So if it is 2 to the power 10, it's kilo. If it is power 20, we say that's mega. If it's power 30, we say it's giga. The values are converted into decimal values as such. And the reason why we have this is because computer memory generally uses a base 2 interpretation. A good example would be if you just double click on your computer and you try to find the properties, you will find that there is a calculation for the used and the free space that is available on your drive. And you can see it's represented both in terms of bytes and bits, bytes and gigabytes. So the long number that you have in bytes, if you divide it by 2 to the power 30, which is kilo, mega, and then giga, that would be equals to 1.84 gigabytes. So that is where we end, and the last two slides are going to be the answer slides. Thank you very much.